Konnichiwa. This is a fun little section on survivorship curves. We have learned about K species, we've learned about R species, we've learned about generalists, we've learned about specialists. Now let's see if we can tie them all together with these curves. So let's take a look. 3.3. So these survivorship curves, they're going to show the number of organisms that are in a population at different ages. When we say survivor, we're saying the amount that have lived past, have been alive for those moments and are still alive. So we're counting for this age group how many survivors exist. How many have made it to this point in a population. So you can see here that our y-axis is the number of survivors. Our x-axis is age. Now, every species has different lifespans. So I want you to look at this line here. The end is what we're going to call the maximum age. Humans, that would be 100, but if we're talking about trees, it could be closer to 1,000 years. The beginning, obviously birth, and then you have your median points in between. But it's important to know that this age is not necessarily a number. It's more like if this is our final, then how can we break it up into chunks between birth and our final? And these are great curves because they're going to help us look at population dynamics to get a better understanding of the reproduction and the survival of those infants as they move forward. All right, let's start with R-selected. We've all learned about R-selected so far. We know that the R-selective species, we often see an age versus survivor graph, something like this. We're going to see it again with our survivorship curves. It's the amount that are making it past a certain age as we go. We learned that previously R-selected are things like trees, moths, things that are producing thousands and thousands and thousands of babies, but they're not parenting any of these children. So not many species are going to make it to that maturity age where they can reproduce again, which is why we have very high numbers in the beginning, but then they drop. Now this is very different to our K-selected species. We're only going to have a few offspring, and we're going to see that there's a lot of work that goes into parenting that offspring. So that offspring is most likely going to make it. Any offspring that is created is going to survive because of this parenting and the amount of energy that goes into caring for this offspring. Now, then we're eventually towards the end of our lifespan, they're going to die off. Now let's look at what we call these different survivorship curves. K-selected, this is a type 1 survivorship curve. R-selected, this is the type 3 survivorship curve. So we're going to look at what's in between as well. Okay, these are our 3 types of survivorship curve. We have our type 1, where we've got very high survivorship of offspring in the beginning until all of a sudden, right at the end of their lifespan, they pass away. That is a type 1. We have type 3, which we've talked about, where very few offspring survive, causing a much lower amount of survivors. So in the beginning, we have such low survivorship, but then once they mature, they're very good at surviving from there. So in these type 3s, that's very low when they're young, but it's very high when they're able to mature and get older. Then we have our type 2. Type 2, I think oysters are a great example of this. Not as many babies as what trees have. And once they have a shell, they normally do a great job surviving. So this is kind of what we call a steady survivorship. It's a steady drop off. We kind of see the same rate every year, every increment in our lifespan, we see the same amount die. It's very different than this type 1 where the death normally happens only at the end. This is like along the way we're going to see death that is constantly happening, but not at the rate of our type 3. Now, we do have to remember, though, that type 2 is on a spectrum between type 1 and type 3. So this type 2 can kind of fall anywhere in between these two. I'm going to show you an example of this a little bit later. So I want to just hone in that piece again about our X and Y axis. So this X axis here is a little tricky because trees are going to live to be like 2,000, 2,000 years old, where our birds may only live to be about 40, 50 years old, and humans are going to live to about 100. So that means this maximum point here is not the same numerical value, but that's okay. We're not using numerical values here. We're just calling this is maximum life, this is halfway through life, and this is the beginning of life. That's how we're quantifying this x-axis, especially when we want to compare different types of survivorship curves. We want to plot them all. They're all living to different lifespans, but we can bring that together, conglomerate it to show the three of them, knowing that start is birth and end is maximum lifespan. Now I want to just throw this in here real fast so you understand the numbering system. If we were to use actual numbers of survival, our graph honestly would look like this for our selected. We are decreasing in population so fast at that birth to infancy stage that it really looks like just like this big L. It's really hard to read anything. So they realized, let's change this to more of a log scaled, where we're talking about by the 10th. Every piece is increasing by the power of 10. So we go 0, then we go 10, then we go 100, then we go 1,000, then 10,000, 100,000. And they found that gives you this nice R-selected type 3 curve here. That it's a lot easier for us to read and to connect. So you may see this number of survivors in either just the straight numbers, but it also may be in this logarithmic increase in our y-axis. Now I wanted to show you this. I actually think it's quite fascinating. It shows you where the human population has come. It's a survivorship curve for different human populations. So let's start. You notice here we have a type 1, we have a type 2 curve, and then we actually, for a human population, we also have a type 3 curve, which is quite rare for humans. But different conditions, different settings, different environmental factors can have a big change on these population curves, and especially our survivorship curves. So this pink one down here, I find so interesting. This is England in the 17th century. So 17th century, we don't have the medical capabilities that we do now. And because most children were used for agricultural purposes, many people had a lot of children because there wasn't a good chance that many of them would survive. So you can see this characteristic drop off here of having lots and lots and lots of children at birth, but then in those first few years of life, they are not surviving past the age of 5, 10, or to the reproductive years. And again, it's due to all these other environmental factors or sociological factors that are impacting this. So we can't forget about that. Now, of course, this type 1 is England now because they do have those medical advances and they do have the technology. And we find that we are able to keep most infants beyond the age of 50. They grow to become that old. It's very likely for that infant mortality rate to be high. And so therefore we're acting a lot more like a K-selected species and like that type 1. However, there are still countries that haven't quite gotten there yet because of instability. And one example here is Niger. Niger is one, this is back in 1999 when this was all recorded, but it was very unstable. And because of those instabilities, because of those environmental factors, whether it was, again, medical conditions or the conditions of water, everything that's going on in that country can cause us to see a constant rate of death throughout the entire lifespan. So just very interesting. All right, well, we get to talk about this more in class, so I will see you all then.